So my name is Frank McKenna. Welcome again to everybody for the next Discovering OpenSees, Surfing the Waves of OpenSees seminar. This one is about adding your code to OpenSees. Again, my name is Frank McKenna. If you need to email me, there's my email address, fmckenna@ce.berkeley.edu. The presentation is available online in PDF form. And when this seminar is over, hopefully by tomorrow, I will have uploaded a video of this presentation. This work and that we do is sponsored by both PEER and NICE through NICECOM, and ultimately the National Science Foundation. So an outline of what I'm going to talk about today. I'm going to give a brief introduction to OpenSees and why OpenSees is designed the way it is. We're going to talk about showing you how to add a new material to OpenSees. I'm going to go through the steps for both adding the code in a Windows environment and a Linux environment. Quickly at the end, I will show you how to add a new integrator using the Unix environment again. It's the quickest way to do it. The steps are exactly the same for Windows. Finally, when we get to the end, we're going to do a quick summary and conclusions. The one thing to note about this presentation right here, I hope I don't get bogged down in the C++ issues. This is not a seminar about how to program in C++. This assumes that you have or you will have or you will be able to develop on your own C++ code or Fortran or C code, as we'll see. And this presentation, what this presentation is to show you how then to take that code and make it work with OpenSees. So quickly on the introduction, just a quick slide on what commercial codes do. OpenSees is not a commercial code. Basically, commercial codes are typically large, complex software containing millions of lines of code. They're closed source in that researchers, such as yourselves, cannot obtain access to the source code. The only things you can do with commercial code is basically add new elements and material routines into the application. They allow you to do that. At least the serious ones do. Not all commercial finite element applications that engineers use allow you to create new elements and materials for the code. One drawback with these commercial codes, again, they're slow to change as hardware changes. In the last 5 years, we've seen a dramatic change in the hardware that's available to engineers, in particular to researchers such as yourselves that you can use. They also don't allow researchers to play with other equally important aspects of the code. I'll talk about what they are on the next slide. And finally, and most importantly from a research point of view, they don't promote sharing of new code. Our community is very bad in sharing code. What we're trying to do with OpenSees is encourage people to share their ideas. Either you can share it one-on-one with one of your colleagues or basically share it with the whole community. So quickly, building blocks for modern simulation. As I say, if we look at a software simulation package like a bridge, what most engineers are concerned about is what materials and elements are provided in that finite element application. But a bridge, like any strike, it's much more than the deck. There's so much more going on. The deck is only a tiny portion of the actual code. The important stuff, what makes the code go fast or what makes it accommodate really large problems, is basically the numerical computation, what solution algorithms, what equation solvers are in the source code. Finally, how do you see what's going on? The information technology. We got databases, visualization stuff. All these things are changing, and they have changed in the last 10 years. Commercial finite element codes are just not able to keep up with these changes, and that's typically just because of the way they allow people to play with these, but the solution algorithms and the equation solvers and how the data is sent to the screen, they're hard coded into the guts of the program. So these monolithic procedural programs are very difficult to adapt quickly to new changes. And one thing I'll say now, and I'll really talk about in my next presentation sometime in a month, is how the hardware is changing dramatically at this time. My current machine is 8 cores. I have access to machines with 250,000 cores. In 5 years, I'm going to access to machines with between 10 and 100 million processors. How am I going to utilize those processors? How are we going to talk to the databases? It's all coming about data. How is the finite element programs going to interface with the data we're getting from experimentation? How do we improve our finite element? It's all about sort of becoming IT, and it's really important that researchers in particular can start playing with these ideas, playing with these things. So the goals of OpenSees, the original goals, basically we wanted to use modern software techniques when we designed the original OpenSees platform. OpenSees, we wanted it to be extensible. We wanted people to, plug and play, try different things. We wanted this finite element application was both for structural and geotechnical engineers, and it had to, be able to change with rapidly changing hardware. We also want to provide a common platform where researchers could test and share new knowledge. Finally, we also wanted a mechanism whereby researchers such as yourselves could get your new ideas out to community. It's really this practicing structural engineers who need new software developments, who need new materials, elements, solution algorithms, equation solvers. They're the people on the front lines. Ultimately, we're trying to get our research to them. The traditional approach of you're writing your dissertations, published in papers, hope that a finite element company is going to pick up on your research and put it into the code. It takes too long. Our community is not moving quickly enough in this regard. Through OpenSees, we're actually seeing that the new ideas are actually getting out to industry a lot faster than in traditional. So how did we do it? To achieve these goals, basically, we developed an open source framework for development of both sequential and parallel applications. This framework we call OpenSees. The framework contains many classes that we originally provided, and there have been many, many more that others in the research community have provided to us that basically allow you to build finite element applications in structural and geotechnical engineering. Now, one of these applications, and the one that basically almost 50,000 people have downloaded to date, is basically the OpenSees.exe, the application that most people think of when they think of OpenSees. They're thinking of this little OpenSees application. As I say, this is an interpreted application. When you run it, it'll take commands or a script. It'll execute those commands, and it'll spit out output. So as I say, OpenSees is a framework. It contains over 1,000 classes or modules. Some of these classes are for basically the finite element method. Some more are for parallel and distributed processing. And then there are additional classes in there for reliability, sensitivity, optimization. But the thing is, these are an awful lot of classes, and we don't expect everybody to understand how they all work. And the nice thing about a framework is that it really doesn't matter to you how all these classes work together, what all these classes are for. All you care about, all you need to understand are those classes that concern you directly. For example, if you're dealing with the material class, all you care about is the material interface. When you're dealing with an element, you care about the material interface and, say, the node interfaces. They're the only classes you care about. You don't care about any other classes. So if you're dealing with the solution algorithm, you don't actually care about how the elements and materials work. If you're dealing with trying to create a new system of equation, you basically don't care about anything finite element. All you care about is how to solve AX equals B as quickly as possible. So to say, you don't have to understand how anything else in the code works. And that's the important thing to remember. I've seen a lot of graduate students spend months trying to understand exactly how OpenSees works exactly so they can create a new element or material. The thing is, you do not have to know that. It's important to get across. As I say, all you care about is the classes you're going to be working with directly. The OpenSees framework contains what are called abstract classes. These are the classes here shown in blue. For example, material, subclasses of material. We have uniaxial materials, n-dimensional materials, and section materials. In addition, there's a whole bunch of concrete implementations that people can actually use. I'm not going to go through them all. There's over 250 different material classes right now. And again, we have element classes. There's an element class. It's an abstract class. It doesn't actually do anything. We've got a whole bunch of implementations, concrete classes. These actually provide different element routines. Again, so integrators. We've both static integrators and transient integrators. There's an awful lot of these concrete classes. When you're writing something new, for example, you're writing a new uniaxial material, all you care about is this class right here. You don't care about any of these other classes in the framework. You don't care about how these other classes are implemented. All you have to do is provide the implementation for this class. So now we want to get your code, new code into OpenSees. How does it work? So if OpenSees comes across an unknown class type in the script, for example, uniaxial material blah, before it actually gives an error message, what it's going to do is it's going to go searching around to see if it can find what's called a DLL, a dynamic library, a DLL in Windows or a shared object in a Unix environment or a dylib in the Mac environment. These are called shared libraries. And what the program can do is it can load these libraries at runtime. While the program is running, it can load up these libraries. And what OpenSees will do, it'll load up, say, the library has to be the same class. The name of the library has to be class.dll, whatever class it's looking for. So if it can't find the library, it's going to open up the library if it finds it. In that file, there has to be a procedure of the appropriate name. If that procedure is there, it will then invoke the procedure. If the library is not there or the procedure within the library is not there, then OpenSees will fail. So what we're going to do today is we want to build one of these shared object libraries. We want to build one of these dynamically loadable libraries so that when OpenSees comes across a material that it doesn't know about, it's going to automatically load it and run it. The nice thing about this is you don't have to build the entire OpenSees program. And another nice thing, if you want to share you don't want to share your source code with anybody, all you have to do is, send your DLL to somebody. So basically, here's what happens. If say I've got this script, Elastic CPP, it doesn't work. The program just fails. So to say to add a new class, we want to do this. We have basically three things we have to do. The hardest, the things that they give you the PhDs for, is basically you've got to provide source code that will meet the interface of the appropriate superclass. You have to write your element or your material. These I cannot do for you. These typically, master's student level or PhD level. This is PhD level work. So once you've got your code written, then you build the library, and then you make it accessible to the program. So there's 3 steps. So before I go on, I'm going to quickly say that while C++ is the main, we're going to talk about C++ here today. C++ is not the only language that is used in OpenSees. It's what I call the glue language. It allows us to use code that's in other languages as well. A lot of the materials and equation solvers are actually written in Fortran and C, and we just call them from C++. So similar to that, your code doesn't have to be written in C++. You can write your code in C or Fortran. The examples I will show you here, the example source code you can download has C and Fortran examples that you can play with. Some people think that C and Fortran are actually easier interfaces to play with. If you're a Fortran programmer or a C programmer, they're probably easier for you to deal with than having to learn the C++ programming language. Right now they only work for adding a new element or a new material. If you want to write any other class, you have to provide the C++ code. As I say, the code you provide, it must meet the interface. If you're writing a new Uniaxu material, it must meet the interface given in Uniaxu material.h file. So if you're writing a new code, you have to provide what's called all these methods. So a quick overview of C++. If the method is defined as virtual, it means that you can rewrite. It means that you can rewrite it in your code. If there's an equals 0 sign, it means that you must overwrite this method. You must provide an implementation. Some of the element routines and some of the Uniaxu material routines are not pure virtual. For example, these methods here are not pure virtual. Standard method, there is code in the repository that will do what's required of these methods. You can take the default. If you don't like the default, because they are virtual, you can override them and do your own implementations. Okay, so adding new code. For those new to programming who have never programmed before, never, ever, ever start with an empty file. No programmer I know actually starts writing new code from just a scratch file. You always take something similar to what you want to do, make changes to that, and make that work. To help you along, we provide basic examples in C++, C, and Fortran. They're available online using what's called SVN. It's a source code revision system. The address for the example code is given right here. It's just svn opensees.berkeley.edu/user local svn opensees trunk developer. When I'm on a Windows machine, which probably the majority of you will be on, the tool I like to use is something called Tortoise SVN. If you Google Tortoise SVN, you'll be able to download it and install it. On this slide here, I'm showing you basically what you do. I'm going to now demonstrate this. So basically, this right now is my home directory. Let me sort of rename the one I did yesterday. So right now, this directory, say, does not have an OpenSees developer in it. So what I want to do is I want to go back one up. And when you install Tortoise SVN on a Windows machine, all you do is you right-click on the directory where you want the code to go, and you'll get these additional Tortoise SVN things in your menu. So if I go SVN checkout, it's going to pop up a window. Now when you get your window the first time, it's actually not going to include this stuff right here. This SVN, this is something I added. Again, I added this yesterday, and it's just because it was there, it takes what was there last. So this is what I added yesterday. It's what I've given on that slide. So this is where the source code is, and this is basically where I want it to go on my machine. So when I've set these two things, I then just hit OK. And basically, Tortoise SVN downloads the example code we provide for building additional classes. So if I now go back into this Peer Center directory, now I have this developer directory with a bunch of stuff in it. Okay? So what's in this directory that we've just downloaded? Well, in developer, there's 3 or 4 files. For Unix users, there's a makefile.def, and some Unix instructions. If you're on Unix, you don't have to do a thing. If you're on a Mac, you have to basically open the makefile.def and uncomment the first line, comment the second line, and then everything works. For Windows users, there's a file, Windows instructions.txt. Open it with Notepad, and it gives you 24 instructions, which are pretty much bulletproof for building a DLL using Microsoft Visual Studio. Also in this developer directory are a number of subdirectories. We have integrator, recorder, material, element. Actually, there's some others. Under material, we have directory CPP, C, and Fortran. As I say, we provide examples in C++, in C, and Fortran. So here's the examples we provided. We also provide in the integrators example. We would say what I'm going to show you today is we've got the trapezoidal method for integration. And one other directory which you don't ever touch is the core directory. That directory contains additional files that are required by some of these other directories. For example, when you create Elastic CPP, you're going to subclass off uniaxial material. When you're compiling uniaxial material, the compiler has to know what a uniaxial material is. Uniaxial material file itself is actually found in the core directory. Elements are similar. In the core directory, we have element, the element.h and the element.cpp file. And then there's some additional files there too. For example, elements need to know about nodes. In the core directory is the nodes. So in core is the minimum set of classes needed. Now for a Windows machine, for Windows machines you need the .cpp and the .h files. For the Unix machines and the Mac machines, you actually don't need the .cpp files, but I provide them anywhere because I didn't want a core for Windows and a core for Linux. Now this current core will always work with 2.3.2 until I make the next revision. So when I update the Windows executable, I may or may not touch files that are in the core. If I touch files in the core, if you update your OpenSees executable to the next executable, the DLL you create with the current core may not work. Hopefully it will. It'll only not work if I change an interface. The interfaces are pretty stable, and they have been for the last couple of years. But every now and again, we need to make a change. They're using OpenSees in a way that we never envisioned it to be used, which means some changes sometimes occur to basically these abstract classes. If that happens, and you've got a DLL, it'll no longer work. It'll always work with the 2.3.2 right now. But if I go to 2.3.3 and I make a change in the core, the DLL you create right now might not work with it. So that's one thing to note. Now to update your core at any time, the nice thing about SVN, let me quickly show it. So here's the developer code. So right now everything is green. That means it's up to date. But if I again right-click on developer, if you want to update to the latest code, all you have to do is SVN update, and it'll automatically go through. And if I've made any changes, they'll automatically be installed in your machine. Okay, back to the presentation. So as I say, there in that developer directory, there's a Windows instructions.txt. If you open it with WordPad, you'll see these 24 steps for building a DLL. I'm going to go through these 24 steps to show you how quickly it is. I'm not going to go in great detail. I'm not going to painstakingly go through it. I have the steps 1, 2, 3 in the presentation. I'm not going to. When I reach that point, I'm actually not going to go through those steps. Basically, here those steps are right here. The one thing to note, you do have to give it the right file name. You do have to give it the right names, the name of the class that you're providing. And one other thing down here, this .. That kind of depends on the version of Visual Studio you have. This was correct for Visual Studio 2005. I believe 10 I'm going to have to add. When I get down to here, I'm going to have to add some more .. You'll see it when I try and work it out what it is. As I say, when I download the developer, that new developer directory, we've got all these subdirectories. We have these files. In the material CPP directory, we have the .h file, we have the source file, and we have a simple example that you can test to see that it works. So why don't well, we'll keep going. Okay, so as I say, in this directory we have these files. We have a source file and we have a header file. The header file is this. This is what is basically in the header file. This will be in your header file. Basically, you can have your class name. Give it whatever name you want. You just can't give it a name that already exists in the repository. So, you know, if you look in the repository, you'll see that we've Stilo 1, Stilo 2, Concrete 01, Concrete 02, Concrete 03 through Concrete 07. Please, 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 when you're naming your files, come up with something somewhat descriptive. Concrete 02 does not really describe what Concrete 02 does. So if you're coming up with the model, you know, use a little descriptive name. Don't be doing Concrete 02, Concrete 03. I failed miserably with some of the graduate students at Berkeley, getting them to come up with meaningful names. Hopefully you people can come up with some meaningful names and put the Berkeley people to shame. So this part here is the material names. These first two methods here are called constructors. The first constructor basically takes the material input properties. This material takes a tag. Pretty much all materials need a tag. And then unique to this material is basically Young's modulus. And I believe this is the strain at which it fails. In addition, we have a destructor. All these methods, as I say, they were in the uniaxmaterial.h file. They all had an equals 0, which means we have to provide them an implementation. So here, I'm saying in this file that I'm actually going to provide that implementation. Finally, at the end, pretty much all uniaxmaterials have these trial strains, trial stress, trial tangents, and the committed strains, committed stress, committed tangent. And they also have some additional stuff. The additional stuff depends on what the material is. This data is unique to each material. This data includes basically the material input parameters, and it also includes state variables for monitoring, what the current state is. In OpenSees, a material or an element has to be able to have the state its current trial step and its last committed step. The last committed step was the last time analyzed. Say you do analyze 1. If analyze 1 worked, all elements and materials, that's a committed step. If analyze 1 fails, like during say a Newmark analysis, we always want to be able to go to the last committed step. So that's why we have these committed values. Sort of during one analysis step, when we're using Newton-Raphson to find the next converge step, we're trying all these different trial locations. So these are our trial values here. So this is the .cpp file. The .cpp file contains two things. Basically, it contains all the source code that implements all these methods, and it also contains an additional method that I'll talk about in a minute. So say we had two constructors and a destructor. The constructor, takes the parameters. So all we do is we're going to set those private variables based on what the input parameters are. And if we need to do any calculation, we do it in the constructor. We also have a destructor. This is the method that's called when the class is actually destroyed, when your object is destroyed. When you do a wipe or you remove an element or you remove a material during the analysis. This class doesn't actually do anything because it didn't actually create any memory. But if you created arrays to store your state variables, this is the time you have to clean it up. One additional important method is this get copy. When you create your scripts, you'll see that you only create, say, one steel material or one concrete material, and then every element, every section and every element uses those steel and concrete materials. Well, we only create one at the beginning, but every section has many unique copies of those materials, and each one has its own unique state. So this is the method here that's used to create all those individual copies. So this is an important method when you're implementing your material. You have to make sure you get it right. For material, typically the hardest method to write is this set trial strain. This is where we're going to set our trial stress, our trial tangent, and our trial strain to be something. So once you've figured out your theory, this is the method that'll take you time to implement. This one here is pretty trivial. All it's doing is setting these trial stresses and trial tangents based on some input strain and some input strain rate. Most materials we have right now ignore the strain rate that comes in. As I say, it's the hardest method for most uniaxial materials. If you look at the existing examples, you'll see this method, this is where all the computation is. If you do all the computation in the set trial strain method, these other methods get stress, get tangent, get strain. They're trivial. You're just returning the trial strain, return the trial stress, and return the trial tangent. So these are trivial if all this computation is done when the material is told that this is its new trial strain. One important method, as I say, during Newmark, if we can't converge to a correct solution, what we want to do is be able to go back to the last happy state that the model was in. So when I want to go back, I'm going to invoke revert to last commit. The element's going to tell your material, okay, go back to your last happy state, go back to your last committed step. So basically, this is all what you have to do. You have to reset the trial strain, the trial tangent, and the trial stress. In addition, if you have state variables, you have to reset them back to be the committed state. Finally, one other method, this is a procedure. That is, we squirrel away in the .cpp file. When I said originally that OpenSees, it'll look for the library, and then what it does is it opens up the library and looks for a procedure. This is the procedure that OpenSees is looking for. It has to have this specific name where it's got the class, and preceding the class is OPS underscore, okay? So what I'm going to do when I open up the DLL, I'm going to look for this procedure. If this procedure is not in even though you create the DLL, if this procedure does not exist in the DLL, OpenSees is going to fail and say that this object type does not exist. So this procedure is very important. So we'll quickly go through it again. It has to have the same, it's OPS underscore and then whatever your class name is. This is what it has to be. Anything else will cause a failure. You have to have the same case as the class. And this case has to be the same as, for Unix users, this case has to be the exact same as the name on your shared library. Now one thing you can do, because I'm going to do this, open this procedure, is if you want to give yourself some kudos, you want to say to anybody who actually comes along and use your work, please reference this work in your writings if you found this useful. You can actually put it so that when OpenSees runs, the first thing it does when it sees your procedure is it's going to say, okay, you're using my code. Please, if you use it, please cite this in any sort of references you provide. So that's one way to get yourself some references. Okay, so once we've got past the kudos, the next thing we're going to do is we're going to look for the material parameters that the constructor needs. So basically, we have to parse the things. So in this case, I'm going to get the first value is a tag. So I'm saying numData is equal to 1. Go get me an integer. Get int input is get me one integer input. And I'm going to store it in iData. The next time I want to get the E and the EYP, so I'm going to get 2 values. So the line will have 1 tag and 2 values. So here I'm getting 2 values. Again, I'm going to store them in an array of size 2. And then finally, I'm going to create my new elastic material with the integer tag and the 2 data values that came in. So so here I'm going to call this basically this method with the integer tag and the 2 doubles that are coming in. Okay. So quickly, and this is all I'm going to talk about this. You can also provide C and Fortran routines if you want. Again, the Fortran is all it's all uppercase, and it's we have an API that you have to meet. If you have a Fortran material that works in some other code, our API is going to be different from their API. the one thing you can do. You could modify your API. That I don't recommend. What I recommend you do is have a look at our CPP file and basically write a wrapper very similar to this that will do the same stuff. If you have problems with this, if you have code that works in some other finite element application and you wanted to get it to work in OpenSees, just send me an email. Show me what your interface is, and I can write you a C++ wrapper to get it in. They're pretty quick and easy to do. A few hours, typically, I can get something done for you. It can be either C or Fortran, but most finite element applications, they'll take a Fortran subroutine. So typically, people ask for more Fortran subroutines than C subroutines. But OpenSees can take either a C subroutine or a C procedure or a Fortran procedure and take care of it. The developer directory contains examples, and that's all I'm going to show up those examples. Okay, so what I'm going to do now is I'm actually going to build a DLL for a new uniaxial material, and we're going to get it running with Windows. The code that I'm going to use is in this developer/material.cpp file directory. It's basically, here's my .cpp file. This is my .h file, the elastic pp cpp. This is my example that I'm going to run to test that it actually worked. And for Unix user, we have a little make file. I'll demonstrate how that works later. As I repeat again, there's a file in the developer directory that contains the 24 steps that you have to follow to get it to work. Each Visual Studio, 2005, 2008, 2010, they're all a little bit different in what they do, but they're essentially the same. I haven't had anybody who's seen this 24 steps and have been unable with their Visual Studio to actually come up with how to build a DLL. So I think that, these 24 steps are pretty much foolproof. So in the slides that I've sent out, there are examples, and I'm going to show you exactly what to do in the slides. 1, you give it a name. 2, you give it a location. 3, hit this. 4, hit that. 5, hit that. I'm not going to go through these slides like that. I'm actually going to do this on the fly. So that's all I'm going to talk about. So these next couple of slides I'm actually not going to go through. So right now I'm going to go do this. So we have this. Here's our materials CPP directory. We have these files. Now we're going to build the DLL. Before I build the DLL, let's just show that I'm just going to show that it doesn't work, to show that there's no magic involved, that I'm not cheating. So here I am in the directory. Those are the files. So if I run OpenSees on this example, as I say, it fails. It cannot find the elastic CPP class that's in this example. Okay? So there we have it, not working. So the first thing I'm going to do is I'm going to start Visual Studio. So there's Visual Studio. So it's File, New. I'm going to create a new project. Create new Visual Studio project. So one of the things I want to make sure it's a Win32 project. It's Win32 and it's a Win32 project. And here I enter the name. This is a very important part. Remember, the name of this has to be exactly the same as the name of the class name. So I've given it the exact same name as the class. This is very important. If you give it a slightly different name, it's not going to work. So you give it the exact same name as the class, and it's going to put it in that subdirectory under CPP. So I click OK. Now before I say finish here, it's very important that we play with the application settings. I want to make sure I'm creating a DLL, and I want this to be an empty project, okay? So we want DLL and empty project. Again, this will fail if you don't hit these two things. So there we go. We now have an empty Elastic PP CPP project. First thing I want to do is I want to add the source files into this. So I'm going to right-click on source files, add existing item. So we have these files that already exist. These files are in this developer materials CPP directory, so I'm going to click up here to go to there. And I'm just going to select the two files that I want. And I'm going to hit add to add them into the project. So I've now added the files to the project. I can try building it. I'll tell you right now it's going to fail. So basically you can't find this file element API.h. As I mentioned, there's a whole bunch of additional files in the developer under the core subdirectory that are required for this to work. So at this point we now add that directory. So if you again right click on the project, go down to the properties. One important thing to do, we want to make sure all configurations, both release and debug, are going to work. So we're going to just hit all configurations. We're going to go to the C++, we're going to hit general. And under the heading additional include directories, we are going to add our core directory. So we're going to hit OK here. So I'm going to try and build this again. As I say, that location is kind of which version of Visual Studio you have. So you can play with it a bit. If you don't want to be playing with the dots, you can provide the full path to where the files are. If you want, you start C:. I typically don't do that, but you can if you want. Okay, so that time it found the core directory, so that worked. What did not work is, now that it's tried to build the DLL, it compiled the two files, but it can't build the DLL because it's missing a whole bunch of stuff. The rather lousy thing about Windows, the DLLs, is that they have to contain all the source code that they need. On a Unix machine, the libraries are what's called dynamically loadable. They don't have to contain all the source code. Once it's loaded into the application, it'll be able to go off and find what other classes have been defined. But Visual Studio isn't that smart. So so when you create a DLL, it needs every single piece of source code that might be called. So we now have to add these to the source files. So I'm going to go add again, existing item again. I'm going to go back up to the developer directory. This time I want to go to the core directory. Now there's two things I could do here. I could go get, okay, it needs uniaxial material, and I could just click say the two uniaxial materials, and one by one go through every single class it needs until it compiles. That will produce the smallest DLL possible. In the interest of time, I'm not going to do that here today. I'm just going to include every single file in core. This will work. I'm basically adding every file that's in the core to our source files. So I can now go build this, build the project. And what it's going to do is it's going to go compile all those other files now. So this takes a few seconds to compile. So that worked. If you're new to Visual Studio, there's two options here. You can have a debug version. You can also have a release version. If you want to share the code with your friends, make sure you give them the release version. Otherwise, it's going to be too slow. Okay, now this failed because it doesn't have that core directory in its So we need to add this back here. Remember this little trick here? If we add that back in, we build this again. Okay, so here we go. Well, you know, build 1 succeeded. We're happy it worked. So if we now go back here and we try to run it, it still fails. And the reason it still fails is because the DLL we just created, it's not in the right location. I could have shown you how to do it, to put it in the right location. I'm not going to. So we're going to come back here. So this is our directory. When we created the Microsoft project, it actually created another directory. In that other directory, we're going to find our DLL. So here it is. So I'm just going to copy this DLL, and I'm going to place it in here. Okay? So I now have the DLL in the same directory as the script. You have another option on Windows. You can actually set your load library path to include whatever directories you put all your DLLs. So they don't always have to be in the same directory as the script. That's something for you to learn about. It's not something I'm going to go into here today. So now that I have the DLL in the same directory as the script, find my you see now that I've run it this time, it actually worked. It found the new material. See, it's an elastic CPU. You know, there's our new material. So it now worked. So that's how you add your new material. Make it work with OpenSees. It's pretty trivial bunch of steps. The hard part, as I mentioned, is coming up with that new file, the CPP and the .h file. So that is Windows. For those of you who are Unix users, and a lot of software developers are, I'm going to quickly show you how to do it. So basically, I'm going to show you how to do it on a Linux machine that has GCC installed. And to do it, I'm just going to use NeaseHub today for this demonstration. NeaseHub is, for those of you who don't know about it, you should log in and have a look. It's a very powerful little place to go on the Internet. You can do lots of cool stuff. Let me just find my browser here. So here's NeaseHub. So I'm going to quickly log in here and show you how to build this on a Windows machine. So I've logged in. I'm now going to go to my NeaseHub. Now this will be pretty quick. The nice thing about NeaseHub is you can have these sessions alive. They stay alive. I'm working on a number of different things. For example, if you're having problems compiling your code and you've logged into NeaseHub, you can actually share your workspace with me. Here's an example of somebody who's sharing their workspace. So it's basically I can type here, he can type here. We both see what's going on. It's very clever. It's very productive to fixing problems. These sessions stay around. So here's basically when I'm in Unix. This is I'm going to download that SVN directory. So again, on Unix, I give the SVN command. Check out the repository. So it gets the source code. If I now cd into developer, cd material, cd cpp, these are the same files that we had before. If I first, just to show you again that it's not built into the executable, I'm going to run OpenSees. This happens to be the location of OpenSees on the hub right now. So if I run it with this example, again, it doesn't work. Unix users, Windows users, watch this. Here I go. I've now built my library. I don't have to do 24 steps. It's just type make. So now if I run the exact OpenSees with that new example, there we go. As I say, we get the output. If you want, remember I was mentioning kudos. There's those kudos appearing once OpenSees starts running. I get OpenSees starting to run, and then the first thing I did is say, this was written by me. I've got use at your own peril. You could have, if you use this, please cite whatever reference you want. It's totally up to you what you want to put in there. You can leave it out if you don't want anybody to know about you. So that's it. As I said, I'm also going to, this directory contains a whole bunch of examples. We said we'd show you how to do an integrator. There's no, as I say, we've got a trapezoidal integrator scheme. Trapezoidal, it's a subclass of a transient integrator. These are the methods I had to implement. They're in the .cpp file. Let's say we have that function, OPS trapezoidal, right here. There's no arguments going in, so it doesn't actually do anything but return a new trapezoidal integrator. I have the constructor, the destructor, and all the methods that are required. So again, on Unix, all you have to do is make. On Windows, you'd have to go through the 24 steps. I have this, they're all called example1.tickle. There's running there's thing with the trapezoidal. And you see it's pretty quick. These machines are very, very fast that you've got access to through NESHub. So if your own machine is pretty slow and you're doing big analysis models, I suggest you run to NESHub and do them there. So that is how to add a new element and a new integrator into OpenSees. If this thing's finished, or should I? Okay. Let me clean up these windows, get to this thing. Anything else I wanted to say? Okay, for next seminar, at the end of February, we're going to be talking about either high-performance computing or how to do soil structure interaction using OpenSees. Again, I'll probably be using the NESHub for the demonstration. So I suggest anybody go out and get you an account if you don't have one. It's free for everybody to use. And with that, I will conclude the presentation.